Okay, so in this video we will make this video very shorter because this is the video about a very important question we will discuss here, and this is from your previous year question and it is asked several times. So this is nothing but what is the Hamming distance, and give the relation between the minimum Hamming distance and the error correction capability. Okay, this relation is very important. And the next thing is the defined Hamming sphere. Okay, what is the Hamming sphere? So from the first question, the definition of the Hamming distance. So in information theory, the Hamming distance between two strings of equal length, from the previous examples, what we have considered that we have always we have taken the code, that strings of equal length, the codes of equal length. If A equals to 2-bit representation, so B is a 2-bit representation. So in this way, I can show you. Okay, in this PDF also here. So if you can see, the length is same. That means if this is 2-bit representation, this is also 2-bit representation. If this is 3-bit representation, this is also 3-bit representation. So for calculating the Hamming distance, we will take all the bit representation same. That means the length of the code will be same. Okay, the strings of the equal length. So in the information theory, the Hamming distance between two strings of equal length is the number of positions at which the corresponding symbols, mind it, it's the number of positions at which the corresponding symbols are different, or the minimum number of errors that could have transformed one string into the other. That means I'm basically calculating the number of positions. How many number of positions are there where the bits are different? So from the previous lecture we were discussing about, this is the first position, this is the third position, the first position bits are same, the third position bits are same, and the second positions we have this dissimilarities between the bits. So that is the number of positions where the bits are different. Okay, different between two code sequences. So that is the Hamming distances. So that is the definition. That means in information theory, the Hamming distance between two strings of equal length is very important. Equal length is the number of positions at which the corresponding symbols are different, or the minimum number of errors that could have transformed the string into the other string. Okay. From the second and third question, so I'm just combining it in answer that given that you have to just give the relation between, you have to derive the relation between minimum Hamming distance and the error correcting capability, and also define the Hamming sphere. So before we go to this question, we have to consider two things. One is K error detecting and K error correcting. So there is two terms, as you can see from the note, that there is two terms. One is K error detecting and one is called K error correcting. Okay. So a code, it's basically the node. So a code C, suppose a code is C, is called the K error detecting. That means you are detecting an error if and only if the minimum Hamming distance between any two of its code words is at least K plus 1. That means what is that? A code C is called K error detecting. You are detecting, not correcting. Okay, so you are detecting, you are just detecting that this code is the error code. This code is the error code, or this, in this positions there is an error. So you are just detecting. So a code C is called the K error detecting. That means we have detected K number of errors. When, what is the relation between this K value, the number of K, the number of detected error, and the minimum Hamming distance? So that is the relation, that A code C is called k error detecting if and only if the minimum Hamming distance between any two of its code words is at least k plus 1. That is number of detected error plus 1. That will be the minimum Hamming distance. Okay. Suppose 0, 0, 0. So it is written that suppose 0, 0, 0 and 1, 1, 1. There is two examples, and the Hamming distance between these two is 3. So Hamming distance. So you know that here it is written that the minimum Hamming distance between any two of its code words is at least k plus 1, where k error detecting. K is basically the k error detecting code. Okay, it's called the k error detecting. That is the number of errors. So if the Hamming distance is 3, then the number of detected error will be 2, because 2 plus 1 equals to 3. So that's why this is satisfying this condition, that is k plus 1. So this is the Hamming distance and this is the k. K is the number of detected errors. Now error detecting means if one bit is flipped or 2 bits are flipped. Flipped means here I'm calculating that I'm detecting the error with respect to this 0, 0, 0, right? So here from this 0, 0, 0, this 3-bit representation, if I flip, flip means if I make 1, 0 to 1, that means if this 0 is 1, consider to be as 1, or flipped to the 1, and again any one bit is flipped to the 1, or you can say that uh, any two bits are 1, 1, so then the error can be detected. Okay, I'm repeating it, that suppose 0, 0, 0 and 1, 1, 1. Okay, so the Hamming distance is 3 and k equals to 2, considering the previous condition. Okay, so error detecting means if one bit is flipped or 2 bits are flipped, the error can be detected. Okay, the error can be detected. That means we will consider that this bit sequence or this code consists error. Okay, if the 3 bits are flipped, that means 0, 0 becomes 1, 1, 1, and the error cannot be detected. So this is a note. So you can take a note that this is basically called the k error detecting. Okay, so k error detecting and k error correcting. So k error detecting, a code will be called the k error detecting code when minimum Hamming distance between any two of its code words is at least k plus 1. Okay. Now, at the second case, I'm considering the k error correcting. Okay, so first is called k error detecting when the Hamming distance is equal to k plus 1. Okay, and for k error correcting, the minimum Hamming distance between two code word will be at least 2k plus 1. So that is the condition. Okay, so that is the condition for any code to be k error correcting, and k plus 1 should be the minimum Hamming distance for the any code to be k error detecting. Okay, so this is two conditions. So first is the error detecting, so k error detecting, and this is the k error correcting. So for the correcting purpose, we will consider this example again consider two code words, that is 0, 0, 0 and 1, 1, 1, and the Hamming space. You know that the Hamming space is a 3-bit representation. So the Hamming space is basically the all possible combination of 3-bit representation. So you know that by 3-bit representation in Hamming space there will be 8 words, like 0, 0, 0, 0, 0, 1, in this way to 1, 1, 1. Okay, so calculating single bit error words respect to 0, 0, 0. That means we will choose this 3 binary representation such that, or in such a way that the Hamming distance